Assalamualaikum and good morning to Dr. Shahrin and fellow students. This presentation, we would like to discuss on probability and statistical data analysis project about the characteristics of the most streamed song on Spotify in 2023. Our group, Kutupat, which consists of me, Atira.
My name is Rauda.
My name is Pavani.
I'm NAZATUL.
My name is AMELIA BINTI AZRUL.
Okay, for introduction, purpose of the study is that the aim of our study is to analyze and understand what makes a song popular on Spotify by examining key musical attributes such as BPM, decibelity, acousticness, appearance in Apple charts, and key of the song. For objectives, our objectives are twofold. We seek to identify patterns and relationships among these musical attributes that explain song popularity on Spotify. And for the second one is that we provide insight. By doing so, we aim to provide valuable insights into the factors contributing to the popularity of songs on these major streaming platforms. For hypotheses, we have several hypotheses guiding our study. We expect to find significant relationship between these musical attributes and popularity songs. Specifically, we anticipate that popular songs will have a higher average BPM. We suspect there might be a correlation between danceability and acousticness. And then we hypothesize that the appearance of songs in Apple charts as a predictor of song streams. Additionally, we expect that the key of songs may influence its average number of streams.
So for the first test on sample, we've employed hypothesis testing, and this is a one sample hypothesis test. So the objective of this test is to determine if the mean bits per minute of a top chart song is equal to 120 bits per minute. And the null hypothesis that we've set is that the mean bits per minute of a song in the population is equal to 120, or mu is equal to 120, and the alternative hypothesis is that mu is not equal to 120. So this is a two-tailed test. And we've used a significance level, or alpha, of 0.05, or a confidence interval of 95%. Our sample size is, or n is 951, which means that this is a very large sample. And so according to the central limit theorem, we can assume that the population is normally distributed. And since we, with that assumption, we can also use the z-test. So the critical values for z alpha over 2 or z 0.025 is positive and negative 1.96, which are indicated by these red lines here. And our test statistic, or z null, is 2.82, which is indicated by this blue line here. And as a conclusion, we reject h null at alpha is equal to 0.05 because the critical value is less than, or the test statistic is greater than the critical value of 1.96. And we have a very low p-value, and so we and it's lower than the significance level that we've set. So we have sufficient evidence at 95% to conclude that the mean bits per minute of a song is not equal to 120. And at a confidence interval of 95%, we actually have an estimated mean of 122.57. This is the point estimate, and at a 95% confidence interval, we estimate that the mean bits per minute of a song on the top chart is between 120.78 to 124.35.
I'm going to explain to you about the correlation analysis between danceability and acousticness. So here we investigate the relationship between danceability and acousticness in song within a 95% significance level. So the variables we use is independent variable, whereby this is danceability, and then the dependent variable, whereby this is acousticness. So our hypothesis statement, which is null hypothesis, rho is equals to 0, whereby there is no linear correlation. And then for the alternative hypothesis, we do is rho is not equal to 0, whereby there is a linear correlation exists. So here, by using the RStudio, we obtain a test statistic whereby t is equals to negative 7.4998. And then the critical values, we use alpha is equals to 0.05, and this is two-tailed test. And for the lower critical value, we get negative 1.9625, and then for the upper critical value, we got 1.9625. And then for the p-value from the RStudio, we got 1.466 exponent negative 13. So if the t is less than negative 1.9625 or t is bigger than 1.9625, then we reject null hypothesis. Otherwise, we will fail to reject null hypothesis. Conclusion here, since t is equals to negative 7.4998 is less than negative 1.9625, then we reject the null hypothesis. So here, there is sufficient evidence to conclude that there is a linear relationship between danceability and acousticness at the 5% significance level. So from the scatter plot here, we can see a lot of the point tends to down here. So it shows a negative slope, indicates a negative relationship. So we can conclude when danceability increase, the acousticness tends to decrease here. When the danceability is increased, then acousticness tend to decrease. And here we got the Pearson correlation coefficient, we got the negative 0.2365461. Okay, and then it shows there is a relatively weak relationship between danceability and acousticness.
Okay, for regression analysis, we use the number of streams versus appearance in Apple chart. Our objective is to determine if there is a linear relationship between the number of streams, Y, and appearance in Apple chart, X, using a linear regression model. For the model type, we employ a linear regression model to explore this relationship. For scatter plot interpretation, upon examining the scatter plot, we observe that the points are moderately scattered around the line, indicating a moderate linear relationship between appearance in Apple chart and the number of streams on Spotify. For the equation, you can see here the regression equation derived from our analysis is y hat equal to 220,445,175 plus 4501330x. Y hat is estimated through the number of streams and x is the number of appearance in Apple chart. For the coefficient, we got the intercepts B0. You can see here the B0 is actually the one from the equation here is 220,445,175, and for the slope is B1 is 4501330. The coefficient of determination R squared for our model is 0.2491. This means that approximately 24.91% of the variation in the number of streams can be explained by the number of appearance in Apple charts. For conclusion, based on our analysis, there is a moderate relationship between appearance in Apple charts and the number of streams on Spotify. This suggests that a popular presence in Apple charts predicts moderate variations in Spotify streams, highlighting the interconnectedness of visibility across different music platforms.
For the ANOVA analysis aimed at understanding whether there exists a difference in mean stream values across various musical keys, our objective was to examine this using a random sample of songs. We formulated two hypotheses for our analysis. The null hypothesis states that the mean stream values are equal across all keys, while the alternative hypothesis suggests that at least one mean stream value differs among the keys. Upon conducting the ANOVA test, we found the following results. The mean of sample means across the keys was approximately 460,620,475.454545, with a standard deviation of sample means around 457,498.215,667. The between group variance was calculated to be 159,077,830,891,951,968, and the within group variance was approximately 214,834,265,331,430,496.00. Our F statistic, which is crucial for determining significance, yielded a value of 0.740467. Comparing this to the critical value of F for alpha value 0.05, which is 1.841891, we found that our test statistic, which is 0.740467, is less than the critical value. Therefore, we fail to reject the null hypothesis. In conclusion, based on our rigorous analysis, we have sufficient evidence to assert that the mean string values do not significantly differ across different musical keys. This finding provides a valuable insight for music professionals and analysts seeking to optimize song performance across various keys on platforms such as Spotify.
Okay, so for this second test of ANOVA, we want to compare this top 300 versus bottom 300 streams. And before I move on explaining the second test, I want to clarify the differences between test 1 on ANOVA and second test. So the first test is the difference actually is the number of samples taken. So for the ANOVA one, we take all the samples. We don't care about whether these streams are top or bottom, we just take all. And the second one, which is ANOVA test, second test on ANOVA is we take the samples based on their ranking streams. So here you can see the table here, which is on the left is the top 300 songs, whereas on the right is the bottom 300 songs. And then we can see that each of them, each categories, we have the number of samples, mean, and standard deviation. Same goes to the bottom 300 songs. And now now we can see that these top 300 samples, we see that we have the mean, standard deviation, between group variance, and within group variance. And you are probably wondering that why the numbers are big. So we're going to go back to the data sets. So data sets, we take the Spotify. We take number of streams, number of listeners on Spotify. And as you know that Spotify, they have million of users. So this number of like the big size of users, which is it can reach millions, it affects our means, standard deviation, this variance, that affect the size of the number for the mean, standard deviation, and variance. So that's why the numbers are big. And for the F statistic test, we got 1.08099, whereas the critical value of F at significant level of 0.05 is 1.86737. And as a result, we fail to reject because the critical value is higher, is more than F statistic test. So that's why we reject. Same goes to the bottom 300 sample. We got the mean, standard deviation, between group variance, and within group variance. And between group variance and within group variance is actually to get the value of the S statistic test. And as a result, as when we plug into this formula, we got 0.75345, whereas the critical value of F at 0.05 significant level is 1.86627. And as for the result, we also reject the null hypothesis because the critical value is, we fail to reject because the critical value is higher than test statistic. And as conclusion, we both see that it indicates that sufficient evidence to claim that the mean of string values did not significantly differ across musical keys between the top 300 and bottom 300. So which means that these keynotes are not one of the main factor that make the streams that affect the ranking of the streams. So yeah, so that's what the conclusion mean.
In Project 2, we analyzed Spotify's most streamed tracks for a better understanding of the popularity of music. Use of statistical techniques such as ANOVA test, regression modeling, correlation analysis, and hypothesis testing, we came at a number of significant findings. First off, popular music frequently deviates from the recommended 120 BPM, suggesting that listeners have different preferred tempos. It appears that tracks that are more danceable also tends to be less acoustic, as indicated by the small negative connection we identified between danceability and acousticness. Furthermore, our research showed a moderate correlation between Spotify streams and the appearance of songs on Apple Music charts, underlining the influence of cross-platform usage on song popularity. It's interesting to note that musical key went against conventional thinking in music theory by having little to no effect on a song's streaming performance. This result offered insightful information to musicians and business professionals who want to improve the appealing factor of the music on streaming platforms like Spotify. That's all for this presentation. Thank you very much.